Hello, my name is Roy Simpson, Professor of Mathematics at Xintercept River College in Sacramento, California. In this video, we're going to be talking about how to use differential calculus to help us graph a function, in this case, a function that actually does have an oblique asymptote. And I specifically chose this example because there are some really subtle hidden nuances within this. So let's go into this. If you need a review of how to graph functions using calculus, please go to the previous video in this playlist, and it should actually cover how to graph a function using calculus. First thing I'm going to do, go back to my algebra days and talk about the domain of this function. This is a function that has no domain restrictions, so I'm just going to go ahead and say negative infinity to positive infinity. Because I know the domain is everything, all real numbers, I know there's not going to be a vertical asymptote. So that will help me out in a few moments here. Second thing I'm going to look for is symmetry. Oh, no, actually, sorry, that's the third thing. I'm going to do intercepts here. Although it wouldn't be wrong to look for symmetry first, but I'm going to do intercepts. When we evaluate g at 0, we get 1 plus e. So that's my y-intercept. Maybe I'll write that off over here, y-intercept. 0, 1 plus e. So it's about 3.718281828459045. And then let's go ahead and set this equal to 0. And you're going to find out very quickly, setting this equal to 0 and trying to solve would require either technology or some more advanced calculus concepts, which if you're taking a course with me, we have not run into yet, but you can actually solve this equation using Newton's method if you already know. However, because it's a mixture of two different types of functions, specifically algebraic and transcendental, or exponential, I should say, it's not possible for us to analytically solve this by hand. So I'm going to not say that, I'm not going to say there's no x-intercepts, but I am going to say that I'm not going to find the x-intercepts. So x-intercept cannot find by hand. That doesn't mean they don't exist, but it just means that I can't find them right now. Now, something that you should note is that this, in the long run, I'm going to note this function does not actually have an x-intercept. But we might be able to actually figure that out. But we'll probably run into some logical fallacy if we try to work on that right now. What's going to happen is when we get to first derivative, you're going to find out that it's going to be impossible for it to have x-intercept. So let's go ahead and move forward for now. 3, symmetry. Again, this function, because it is a mixture of algebraic and exponential, I'm going to say there's no translational symmetry, but I'll still go ahead and look at g of negative x, which is 1 plus x plus e to the 1 minus x over 3, which I cannot manipulate in any way to plus or minus g of x. So in other words, it's not even nor is it odd. So no symmetry. Okay. Real quick, right? And now let's see, other things I'm going to take a look at. Asymptotic behavior. So I know there's no vertical asymptote because there wasn't a domain issue. The next thing I'm going to think about, though, are horizontal asymptotes. Now, to have a horizontal asymptote, the limit as x goes to positive infinity or the limit as x goes to negative infinity must be finite. Well, let's take a look at the limit as x goes to positive infinity to check for a horizontal asymptote. Now, some instructors will just say, well, I'm okay with you just saying that there's no horizontal asymptote. However, I don't know your instructor, and this is a fun, good, robust problem to do. to really showcase that you know how to take a limit as x goes to infinity. So I'm going to take the limit as x goes to infinity of 1 minus x plus e to the 1 plus x over 3 power. And if you take a look at that, I'll go ahead and break out the 1 because there's no real reason to have that in there. So I'll say that's 1, I'll factor out a -2, minus the limit as x goes to infinity of x minus e to the 1 plus x over 3. If you look at that, that is of the form infinity minus infinity. Now, you should have, in any good calculus class, you should have already covered something called Lhopitals Rule. This infinity minus infinity can be transformed into an indeterminate form that you can use Lhopitals Rule on. Remember, you cannot use Lhopitals Rule on infinity minus infinity form, but you can if the form becomes 0 over 0 or infinity over infinity. So what I'm going to do here is a pretty hefty trick, actually. A lot of people will not have thought about this, but I am going to say, well, that's the same thing as the limit as x goes to infinity of, and I'm going to factor an x out of this. So again, this is a bit of a trick, something that I don't think a lot of people would see, and so that's why I'm doing this problem. Now, I also want to mention that I'm not splitting this limit. I'm going to evaluate the limit as x goes to infinity, the product of these two functions. However, I am going to look at what is the limit as x goes to infinity of 1 minus e to the 1 plus x over 3 over x. I'm going to look at that because I want to see what does that tend to. I know what x tends to. That first factor right here will tend to infinity, but I need to know what does the second factor tend to. So as an aside, I'm going to look at the limit just to see, as x goes to infinity, what does 1 minus e to the 1 plus x over 3 divided by x tend to? Well, I could tell you that's the same thing. Again, if I were to take a look at this kind of in a separate format, it'd be the limit as x goes to infinity, 1 minus, the limit as x goes to infinity of e to the 1 plus x over 3 over x, and that would be infinity over infinity form. So that's indeterminate of form infinity over infinity. So I can run Lhopitals on that just to see where this is heading. So via Lhopitals, this heads to 1 minus the limit as x goes to infinity of, again, 1/3, because that's a derivative of the numerator, 1/3 e to the 1 plus x over 3, and the derivative of the denominator is 1. Now, as x runs off to infinity, that limit will be infinite, or in other words, this would tend to negative infinity, 1 minus infinity or negative infinity. So let me go back to this problem. This is going to tend to 1 minus, again, as x goes to infinity, this tends to infinity, and this tends to negative infinity, but they're a product. That's all I care about. It's infinity times negative infinity. So, and there's a minus sign in front of it. So it becomes to a plus infinity, or in other words, just infinity. I did not actually split the limits. All I did was just see what a piece of that goes to. If they both tend to infinity, it's perfectly fine to work like that. So I happen to know that as x goes to infinity, this function blows up to infinity. I can do the same work, by the way, as x goes to negative infinity. I'm not going to, but I could. The reality is that there are no horizontal asymptotes. Okay. So now I need to ask, are there any oblique asymptotes? Well, let's take a look at the function. And I think, just intuitively, there is an oblique asymptote because this picture right here, not as x goes to positive infinity, but as x goes to negative infinity, that picture will tend to 0. So I know, because e to a negative infinite power is going to tend down to 0. So I know that as x goes to negative infinity, what gets left over is 1 minus x. So there is a pattern to g of x as x goes to negative infinity. As x goes to positive infinity, it's just 1 minus x plus infinity. That's not worthwhile for us to investigate. But if it's going to be 1 minus x plus 0, well then it acts just like 1 minus x. So my claim, and I'll write this in blue here, claim is that y, which is equal to 1 minus x, is an oblique asymptote. Most people, again, would call this a slant asymptote, but I'm going to call this oblique just because it's more general. Oblique asymptote as x tends to negative infinity. And so let's go ahead and do a proof of this. And you can go back 1 or 2 videos in this playlist to see why I need to go through this proof, but because I define oblique asymptotes via calculus there. Proof, by definition, if it's going to be an oblique asymptote, we need to look at the limit as x goes to, again, we're going to negative infinity here, of g of x minus what my supposed asymptote is. I want that to be 0. Well, let's see. That's going to be the limit as x approaches, again, negative infinity. G of x here is 1 minus x plus e to the 1 plus x over 3. And I'm going to subtract y. And y was 1 minus x. Let's see what that is equal to. Let's see, the 1's cancel and the negative x plus x, those cancel. And so you have the limit as x goes to negative infinity of e to the 1 plus x over 3. And to be rigorous, let's go ahead and do this. This is the same thing as the limit as x goes to negative infinity of e times e to the x over 3. That's e to the first times e to the x over 3. And I can factor that e out. E times the limit as x approaches negative infinity. And I have e to the x over 3. As x goes to negative infinity, we actually have previous theorems that tell us this is true. As x goes to negative infinity, this tends to 0. QED, that tells me that my claim is true, that actually it is true that 1 minus x is my oblique asymptote as x goes to negative infinity. So I'm going to put that in my list of information here. I have my y-intercept is at 0, 1 plus e. I can't find my x-intercepts, but I do know I have an oblique asymptote, y equals, 1 minus x? Again, as x goes to negative infinity. That'll help out in the long run. Okay. All right. So that was probably the hardest part of this problem. Now we're going to go ahead and deal with the small stuff here. So let's see, what step would we do? Call this step 5. Step 5 is all about what is g prime. So g prime of x. Well, remember g of x is somewhere in here. I'll highlight it. It's this piece right here. That's g of x. So take its derivative, and that'll be a negative 1 plus 1/3 e to the 1 plus x over 3. And we want to see when is that 0. So, and when does it not exist? Well, I happen to know that always exists, but g prime is equal to 0 when? Well, when 3 is equal to e to the 1 plus x over 3, right? All I did was set g prime to equal 0, add 1 to both sides, and multiply both sides by 3. Take the natural log of both sides. So natural log of 3 is equal to 1 plus x over 3. Subtract 1. So that will imply that we have natural log minus 1. And might as well just say multiply everything by 3. There we go. So I know that my derivative is 0 at that point, whatever that point is. Again, I'm not going to use a calculator. I haven't touched a calculator this entire time. G prime. There's no symmetry, so I'm using the entire number line here. But I know that G prime is only 0 when x is whatever that is. Now, just to remind ourselves, natural log of 3, that's greater than the natural log of e. Natural log of e is 1. So the natural log of 3 is slightly larger than 1. So therefore, this value is slightly larger than 0, which means that this entire value is also slightly larger than 0. So I'm going to go ahead and say the x value, and I'm going to mark 0, but that's not actually me saying that the sign for the derivative changes there. I'm just marking 0 on my number line. I'm going to place, maybe right about here, the value 3 times the natural log of 3 minus 1. It's a positive value. That's all I know. Now remember, my number line is broken into only 2 pieces here. That plotting 0 is just for me seeing where 0 is. In fact, maybe I should erase that. Okay, and I'll erase this here too. But there is 0 to the left. All right, so let's figure out. Let's plug in any value into the derivative below this 3 natural log of 3 minus 1. And so I'm going to go ahead and plug in, let's say, a negative billion. Okay, so G prime of negative huge. Oops, that's not how you spell huge, by the way. Huge. Well, that's negative 1 plus 1/3 e to the 1 plus negative huge over 3. Now, that negative huge over 3 e to that power is roughly 0. So this is going to be negative here. And then over on the other side, G prime of huge. Again, you might want to actually plug in something. But to me, it's easy just to visualize. I'm plugging in a billion into this derivative. If I do that, I get a very hugely positive number and minus 1. So it's still going to be hugely positive. So I know that my derivative tells me my function is decreasing, and then it goes to increasing. And so I have, going from decreasing to increasing, I have a local min right here at 3 natural log of 3 minus 1. Because again, I'm not allowing myself a calculator, I'm going to have to evaluate the function at that x value to find out what the corresponding y value is. It might be a bit of a mess, but again, we're in calculus, so we should be used to some long-winded problems here. So to find point for the local min, evaluate g of 3 times the quantity natural log of 3 minus 1. And remember, g is, if I scroll all the way up, it's 1 minus x plus e to the 1 plus x over 3. So 1 minus this value 3 natural log of 3 minus 1 plus, I think it was plus, yeah, e to the 1 plus that number over 3. E raised to the 1 plus that number over 3. So that number is 3 times the quantity natural log of 3 minus 1 over 3. I'll go ahead and just mention, well, maybe I won't. Maybe I'll just evaluate this. Let's see. I'll get a negative 3 natural log of 3. I have a positive 3 plus another one is plus 4. Plus e to the, these 3's cancel. I'll have a natural log of 3 minus 1. The minus 1 positive 1 will cancel. I'll have an e to the natural log of 3, which is 3. So this is going to be negative 3 natural log of 3 plus 7. Oops. It's not negative 3. Yeah, it is negative 3, natural log of 3 plus 7. My ultimate question is going to be, is that positive or negative? And I know that the natural log of 3 is just slightly larger than 1. So multiply that by a negative 3, and you have a number that's slightly less than negative 3, maybe negative 3.5. But the reality is this is going to be a positive number. And that's going to play a huge role when I go to graph. Okay? So maybe I should, again, write this in my list of information. In fact, my list of information is getting kind of long up above. So I'm going to write it off to the right-hand side really quickly. So I'm going to scroll over to the right, and I'm going to write down all of my information that I gathered earlier. And you can see, I mean, I just kind of quickly jotted things down, but this kind of encapsulates all the information we had written up above, I think. Let me just double check. Oh, I have an oblique asymptote. That's right. Y is equal to 1 minus x. That's going to be important, so I'll write that in there. Oblique asymptote, y equals 1 minus x, and that's as x goes to negative infinity. Okay. Let's see what else we have here. Okay. Now we're going to go to the very final step, which is about concavity. So step 6, or whatever step we're at, g double prime. Let's take the second derivative. Now we have the first derivative staring at us right here. So the second derivative is going to be actually a 1/9 e to the 1 plus x over 3. So 1/9 e to the 1 plus x over 3. G double prime is never 0. G double prime is always defined, right? This is never going to be 0. So G double prime is never 0. It's always defined as well. So drawing a number line, and we can use any number we want to plug in a G double prime to figure out the sign. And the reality is, because it's an exponential function, the coefficient's positive, I know it's always positive. So in other words, it's always concave up. So let me write that over here. Concave up on negative infinity to positive infinity. So that's my information that I'm going to use. And so let's go ahead and tackle this. Instead of drawing the number lines up above, which I've done in the past, I'm just going to just jump right into it like this. Okay. Now I happen to know when x is 0, the value of the function is 1 plus e. Now remember, 1 plus e is 3.7 roughly, so I'm going to park that right here. I happen to know that as x goes to negative infinity, according to my information off to the right here, as x goes to negative infinity, I have this oblique asymptote. Now this is often very difficult for me to draw in, but it's a shifted, it's a y equals negative x, but lifted up 1. So let me go ahead and draw that in here as carefully as I can. To be honest with you though, my graph will not do it a lot of justice. But here's my oblique asymptote. It's just a guideline. I happen to know that as x goes to negative infinity, my graph wants to match with that. It's concave up always, and it's going to be decreasing until I get to 3 natural log of 3 minus 1. Remember, 3 natural log of 3 minus 1 is positive. Okay, that's all I care about. It's going to decrease until I get into the positive x values. So it's decreasing on the left-hand side here, and it's concave up. That's what I'm concerned with. So it's going to look something like, and I'm going to hash this out. I hash it out like this because it's just a lot easier to deal with, honestly. Okay, so notice that is decreasing. It's concave up. And slightly, a little bit after x equals 0. Not too far after, because that 3 natural log of 3 minus 1, that's just very slightly above x equals 0. So at some point, right past x equals 0, I'm going to have a minimum. So I'm just going to go ahead and draw a little bit further here that it's decreasing. And then I'm going to mark a point. And I'm going to say that point. I know it's arbitrary, right? But I'm going to say that that point right there is the point. Well, I'm going to have to actually go over here and let's see, we have this local minimum right here, right? So I'm just going to go ahead and copy that and paste it over here. I know that. Don't you wish that you could do that on an exam, right? Just make life easier. Okay. So that point right there is 3 natural log of 3 minus 1, which is slightly positive, comma, the y value is going to be 7 minus 3 natural log of 3. Again, as I just said a few moments ago, natural log of 3 itself is slightly greater than 1. So negative 3 times that, slightly less than negative 3. But 7 added on to that, still positive. And then from this point forward, from 3 times the natural log of 3 minus 1, we have an increasing function. It's always concave up. So it's going to be increasing, but concave up. And it blows up to infinity. There's no oblique asymptote on that side. So using calculus, this is what I think the function is going to look like. Now I'd like to compare that using Desmos to the actual graph of the function to see if we're even near to being correct. And this is the graph on Desmos, and I would have to say that is pretty close to what I have, right? That is pretty awesome. So there you go. There's a little bit of calculus with some asymptotic behavior. Again, I highly recommend that you watch the next videos in the playlist or the previous videos if you need to review this information.